Alright, so my presentation is on membrane potential and Ohm's law. This is a diagram of a neuron. So these are the dendrites. They receive signals from other neurons as neurotransmitters, and then those signals are incorporated and summed up in the cell body, which then transmits those signals as an action potential down the neuron. And then that action potential goes across the length of the axon until it reaches the axon terminal, where it causes the release of more neurotransmitters into the postsynaptic cleft, which is the area between the axon terminal and then the dendrites of the next neuron. So since the axon is kind of acting like a current carrying wire, what we can do to improve the flow of the current is increase the diameter of the axon or decrease the resistance. But since cells can't really afford to do that, they've evolved to have myelin sheets, and that's because of glial cells, which attach themselves to the axon and secrete these myelin sheets. So the myelin sheets also act as insulators to prevent the leakage of current, or otherwise known as the ions. And the area in between myelin sheets is called the nodes of Ranvier, and they actually help propagate the signal at a much faster rate since there's less resistance in these areas. So this is one side of a axon membrane. So as you can see, we have a lot more sodium ions on this side of the membrane, and thus a lot more positive charge. And then you have more potassium ions on this side of the membrane, though there's less overall positive charge. And this difference in positive charge is what actually gives neuron cell membranes a negative membrane potential, and that's relative because the inside of the cell is more negative relative to the outside, which is obviously more positive because of the positive ions. And then we also have 3 voltage gated channels. We have a sodium channel, a potassium channel, and then a sodium potassium channel. So what happens during an action potential is that usually a cell's resting potential is around negative 70 millivolts, and at around this membrane potential, the only thing open is the sodium potassium channel, which pushes more sodium out and pushes potassium in by passive transport. But in order to start the action potential, the cell actually has to actively push. The cell actually has to actively take positive charges in near the axon hillock, which is near the cell body around here. Once a certain threshold of negative 55 millivolts is achieved at any point around here, the sodium channels open. So the sodium channels opening causes a lot of sodium ions to rush into the cell because there's less positive charge on the inside, and there's less sodium ions inside. So that creates an electrochemical gradient for the sodium ions to rush in. And then once they reach a certain potential, they depolarize the cell membrane from a negative potential to a positive potential. Once a certain positive potential of around 40 millivolts is achieved, the sodium channels close and the potassium channels open. So since there was already more potassium ions inside the cell, and now there would be a lot more positive charge inside the cell as well. That electrochemical gradient rushes potassium ions out of the cell, and that's why we see this curve where the cell is repolarized to a negative membrane potential, and it actually goes past the cell's resting potential, and this is what gives it what gives neurons a refractory period, which explains why they cannot just keep constantly firing. Yeah, so once once potassium ions keep exiting the cell and create a negative membrane potential, which will be more negative than we want it to be. The potassium channels also close, and then the sodium potassium channels open. So then these work to bring the neuron back to its resting potential by bringing potassium ions in and sodium ions out. So that would bring it back to the resting potential of -70, and then the cell is ready to go through another cycle. All right, so how this all relates to Ohm's law. So Ohm's law equals voltage. Ohm's law is voltage equals current times resistance. So we can rewrite that using conductance, because conductance is the inverse of resistance. So we can rewrite that to voltage equals current over conductance, which we can use to derive a formula that we use to measure current with respect to conductance and voltage across the cell membrane. So this equation says the current of ion X equals the conductance for ion X times the membrane potential minus the Nernst or equilibrium potential for ion X. And so what the Nernst or equilibrium potential is RT over ZF times the natural log of the concentration of ion X out over the concentration of ion X inside the cell, or inside the neuron. So R stands for the gas constant, Z is the valence of the ion, T is the temperature in Kelvin, and F is Faraday's constant. So this equation overall gives us the chemical gradient for ion X, and the membrane potential gives us the voltage gradient for ion X. So overall Vm minus Ex actually gives us the electrochemical driving force for ion X. So we can use that to calculate the or measure the current for ion X. Oh, and I had a lot of fun in your class, and I hope you have a nice break.